topic today is to look at an important part of, and it's the last part of the number theory, which is something called the discrete logarithm, right? And before looking at the discrete logarithm, I'd like to do something first. So let's look at, remember, what is a logarithm in general, without looking at discrete numbers or integers, just general in real numbers. What was the definition of a logarithm? When you say log x to the base a, what does this mean? What is the meaning of this? ده مقصود عشان ما تشوفوش. So log, خلينا نكتب بلون فاتح شوية. Log x, yes, you were saying what, Ali? By, definition. What?
Get the number x. What power do we need to put for it?
Exactly. So basically, the resultant from this, let's call it y, means that if you take a to the power y, you will get x. It's the power to which you raise a, right? The base of the algorithm, so that you can get the number x, correct? Right? Okay. So if I write this, a to the power of log x to a, what's gonna be the result? اللي هي x, right? So again, a to the log of x to the base a is equal to x مباشرة, صح? Because raising to the power is the inverse operation of taking the logarithm, as long as you maintain the same base. So this is the base of the power, and this is the base of the logarithm, right? Okay. And again, this follows directly, as you said, from here. You can just remove log a to the power x to y, and the result is that a to the power y is equal to x, so this is equal to x, okay? Okay, so that's per the definition. What are the most important features of the logarithm, right? First of all, logarithm of 1 to any base is equal to?
No, the base 0.
0. Anything raised to the power 0 is equal to 1. Right? So log of 1 to the power a, regardless of what's a, is always equal to 0. Log of 0 is a number that you cannot calculate. It's minus infinity. It's not defined. You cannot find log of 0. Okay? And then what are the other properties?
You can take the
Log of a,
power, you can take it out.
x times y. This is equal to?
The addition of log x.
Yes, so log x base a plus log base a y. And log a x to the power y is equal to?
Y log x.
Exactly. Y multiplied by the log of a of x. Log to the base a of x. Tamam? Okay? So these are more or less the general properties of the logarithm, right? If you divide, what happens? So the addition becomes subtraction, okay? Okay, now we are now looking for a function in discrete domain. In discrete domain means that all the numbers that you use and all the results that you get are going to be integers. So we are not, generally the log, and most of the time it gives you non-integer number, right? Now we are looking for cases in modular arithmetic where we can raise something to the power of a particular integer value to get a third integer, right? Within the same modulus. And then we know in that case that that power that we raise to is the log of what we get on the other side, right? Did you get what I mean or not? طيب. We are gonna rely a lot on this definition for the logarithm in order to figure out the logarithm in discrete domain, okay? Let's see how. First of all, let's discuss powers of integer, any integer a mod n, okay? Euler's theorem tells us what? That a to the phi n, right? where phi of n is the Euler's tangent function that I just reminded you with, right, is congruent to 1 mod n under the condition that a and n are relatively prime numbers.
This is not
Okay.
new.
This is something we know before. Now we can generalize that we can find an integer m, not necessarily equal to phi of n, okay, such that a to the power m is equal to or congruent to 1 mod n, okay, for the case again that a and n are relatively prime. Is this true? It's always true because there exists at least one solution to this. What is the solution? Nah, this guy. Right? If I say a to the power, خلينا أغير الcolor. A to the power m congruent to 1 mod n, okay, and a and n are relatively prime. Okay, I'm saying that this relation is always true, right? What is the case that we know that it exists for when m is equal to phi of n, right? This from Euler's theorem, right?
طيب.
So there is at least one solution to this. But in fact, in general, there might be more than one solution.
What are the other solutions?
Okay. Other solutions are some integer numbers, m, with some integer values. Okay?
They're not the phi.
They are not the phi. They might have some other solutions. You might not have some other solutions, right? Okay? But in general, we can write this expression as a general true statement. Worst case scenario, it will be true under the special case that m is equal to phi n.
Why
Okay?
do you need to generalize?
Yes.
What is that sideways E?
There exist. There exist. That's a mathematical expression, means
Why is it
there, it's written this way. Like when we say, for example,
X جزء من R مثلا.
you know, when you start a proof and you started with this.
Doctor, for us it was like a, it wasn't like an E, it was like a curved shape, yeah. That's it, yeah.
Like there is, that's element of or belongs to. That's a different story. No.
Oh.
This says, this reads at, there exists at least one m.
Sure.
So this is read in English as there exists and then something. Okay? That's,
So why do you need to generalize?
now we'll see why. Okay? But we can generalize, right? Okay. Now if we go for an integer a and try to test this through different scenarios, like using different mod numbers and using different integer values, okay? Especially for prime numbers, we will find some interesting properties that in some cases, okay, especially for prime numbers, in some cases, we will have only this. So for certain choices of a and n, we will only have the phi n as the only solution. For some other choices of a for the same n, we might have a few values of m, but the number of possible values of m, okay, is less than the size of the modulus.
Okay.
And in some cases, extreme cases, the number of possible values of m is equal to the modulus itself. Okay, so m can be 0, 1, 2, 3, 4, up to p minus 1, if this is a p, a prime number. Okay?
What does that tell us?
We are moving one step at a time. In the case that, first of all, the highest possible value for m is going to be the phi n. Tamam? Regardless if you have multiple solutions or not, within those multiple solutions, you will have different values of m. The highest possible is the phi n. Okay? This is by default because, again, how many numbers are there? Mod n, it cannot be greater than n, and phi n is not greater, is the largest possible before you reach n, so the highest possible value for this m is phi n. The second thing is, in the case that a, the choice of a, okay, gives me n minus 1 solutions for this, okay, يعني معناها انه this for a to the power 1, okay, I'm gonna have this, and for a to the power 2, I'm gonna have this, and for a to the power 3, so that for different values of m, I'm gonna have this. We call a primitive root of n, okay? Sorry, doesn't give me, sorry. You said the highest possible is phi n, so m, the largest possible number of possible values for m, is phi n itself, okay? So in the case that the choice of a will give me possible values of m that reaches phi n, in that case I call a primitive root of the number n. Just definition.
In case m matches phi, then a is primitive root.
In case
M matches phi. Like
not matches phi.
I'm equal.
The number of possible values of m
is the same as
is equal to phi.
Equal.
مش a equal to phi, مش m equal to phi. No. It's the number of m can have more than one value, right? The number of possible values for m is equal to phi n.
يعني let's say 5n is 5 مثلا. So m has 5 different solutions or 5 different possibilities.
Yes. So m have 5 different
That's
possible
a very
values.
weird relation
Okay.
to find out.
Yeah, but it's very important. Okay. Any questions so far? Okay. Let's look. I think here we have a table that will allow us to see these things in numbers. Okay. So let's look. All this table has been established mod 19. 19 is a prime number. For a prime number, what's the value of phi n? What's the value of Euler quotient function?
Can I 1 minus?
Yes. So it's prime number minus 1, which 1 minus.
Okay.
So phi n in that case is equal to p minus 1. So in this case it's 18, right?
Yeah.
So the value of phi n is 18, which means that for a primitive root, how many possible values we will have for m? 18, right? So we will see those and the ones that reaches the whole thing, right? So let's check. In the first row, okay, let's choose our a as 1, okay? Of course, 1 raised to any power is 1, right? So in that case, there's only, what do you say? There's only one possible value, 1, right? Okay. Now let's go to the second case. If a is equal to 2, okay? 2 to the power 1 is equal to 2. 2 to the power, that's mod 19, right? 2 to the power 2 is equal to 4, mod 19, that's 4. 2 to the power 3 is 8, mod 19 is 8 as it is. 16, 2 to the power 4, mod becomes 16 as it is. 2 to the power 5, 2 to the power 4, 6. 2 to the power 5 is how much? 32. 32 mod 19 gives you 13.
So
you believe that or you calculated it?
No, I mean it's until you get 19 and then you restart again.
Yes.
So this is
yeah, exactly. So 13. 2 to the power 6 is, what's 2 to the power 6? 64. 64 mod 19 equals? Huh? مكتوبة.
50.
64 mod
56.
19.
56.
64 mod 19. The remainder of dividing 56 by
7
19.
yeah.
It's 7.
Oh,
You believe that?
أنا
or you
حسبت
don't?
العكس يعني. I don't know.
64. What is the remainder? What is the mod operation? So we want to calculate 64 mod 19. Okay, what does this mean? It's the remainder of dividing 64 by 19. That's the definition of mod, right? Okay, so what's the remainder of dividing 64 by 19?
64 minus. There are 3 19s in 64.
Yes.
And the remainder is
7.
3 plus 4.
3 plus 4 اللي هي ايه؟
الفور اللي هي 60
the remainder is 3 in every one of them ولا ايه؟ انا مش فاهم يعني ايه؟
64 is 60.
Okay.
بعمل 20 و4
Yes, خلاص I got the idea. Yes. Okay. So the remainder is going to be 7, right? Okay. And then 2 to the power 7 is equal to how much?
128.
128. What's the remainder of dividing 128 by 19? If you calculate it, you will find it's 14. You keep doing this. Notice that in any one of those, there is no repeated value, right? So there are distinct possible values, right? Okay. So the number of possible values that gives you different outcome on the mod operation is equal to actually phi n completely. So this base, which is 2, is a prime,
Primitive root.
primitive root of 19. Okay?
In this case, there are 4.
4a. Exactly. This one, this one, this one, 6. This one, this one, this one, 6. I don't know, 6. Okay? So in this case, you will notice that the primitive roots, the ones that have m's generating distinct values, of course you can put any value to m, but we are talking about how many values of those m generates distinct outcome when you raise it to the power m, when you raise a to the power m. Okay? And you will find that the total number in these particular cases is equal to 18, which means they are primitive roots. In the other ones, you will notice a very nice property, right?
Repeating.
Exactly, it's periodic. So look at this one, for example. Best example here because it's very short, okay? So 7 raised to the power 1, mod 19 is 7. 7 raised to the power 2 is,
This hour bringing
49. Mod 19,
that.
the remainder is 11. 7 raised to the power 3, 343. Okay, 343 mod 19. You believe it's 1,
Wow.
right? And then if you go after that, you will notice that the whole thing repeats again, and then it repeats again. There is a reason why it happens, right? Because once you reach 1, then you multiply by something, it becomes as if you are multiplying by 7 again, because this whole thing, mod 19, gives you 1, right? Then when you multiply it, it becomes as if it's 7 mod 19. And then it's like 1 multiplied by 7, so that's 7. And then here it's 7 squared mod 19, here it's 7 cubed mod 19, and then you repeat again, and so on.
Actually, all of them, all of them end with 1.
Always, that's another property. When you do that operation, all of them are gonna end up with 1. Either one time, if it's a primitive root, or somewhere in the middle, and then repeat. Okay?
So you just have to check the number after 1. Does it repeat or not?
Yeah.
If it's repeating, then it's not the primitive.
No, you just need to check everything before 1, and if the total count with the 1 is equal to 18 or equal to p minus 1, then it's a primitive root. Okay? Okay. So now we figured out this. All of this was just to define what's a primitive root. Okay?
How do you need, why do you need?
Why do we need? Okay. Definition of discrete logarithm. So discrete logarithm can only be calculated, okay, for a number p, for a base p, okay, and for a number a which is a primitive root of p. If the number a that you choose is not a primitive root of the mod or the modulus that you are using, then you cannot calculate a discrete logarithm in that case.
It's a definition.
Yeah. The reason is if you try to calculate a logarithm in that case, it will not be an integer number. So you cannot use it. Yeah. Sorry? Yeah, it will be something outside the integer range, right? So only for the cases that, number 1, we do it only for modulus prime number. Number 2, we can do the logarithm for a number, an integer number a, which is a primitive root of that modulus. Okay? And in that case, the definition is if we can write that b is equal to or congruent to a raised to the power I, okay, mod p, remember, this and this have a certain relation. What is it?
Primitive root.
Yeah, a is a primitive root of p, and p is a prime number, okay? Now, if we can write this relation, this means what? What is the meaning of I in this case?
It's the log value.
Yeah,
No.
it's the log of what?
It is the number of. It is the
I is gonna be the log of what?
log of a in b.
Hmm?
Log of b
yeah.
minus.
Yeah, doctor, it's how many times you multiply a until you get to b?
Where is gonna be our base of the logarithm in this case?
It's a.
A,
Yeah.
صح? And what's gonna be the logarithmic value?
B.
B. تمام. So in that case, this is the log, and we call it the discrete log, okay? And it's for the base A, and we have to say that it is for the modulus P. So in that case, we have two bases to the logarithm, the modulus that we are using for the calculation, and the actual base, the actual exponent, okay? And the log here is gonna be log of what?
B.
صح?
Yeah, but doctor, it's always divided like the first number is the primitive root and the second one is the modulus, right?
Yes. The first one is the base.
The
And the second one is the modulus, and the base and the modulus, the base must be a primitive root of the modulus. Okay? Any questions so far? That's how we define the discrete logarithm. Okay? So if I want to calculate a discrete logarithm for a specific integer b, and I want to calculate it modulus a prime number p, and for a base a, which is a relative, prime, what do you call it? Primitive root of primitive root of p, right? Then that is what is the solution for this equation. This logarithm, okay, is the solution for this equation, is the I. Okay? Tamam?
Doctor, what does it say here at the bottom? I couldn't understand.
Yeah, okay. It says that if you try to, again, even for real numbers, calculating the logarithm is not an easy task. You cannot do it by math derivation, right? And the only way we do it before calculators was we have tables that have been numerically calculated for those values.
So someone sat down and did it.
Using some approximation formulas.
Okay.
Right? The only other way is to start like, okay, saying, okay, I need the logarithm for a particular number. Let me go through the exponents, for example, incrementally in discrete values. And then I keep raising. Now, the last one was, for example, to the power 5.
Value,
Yeah, and the next one was to power 6. Power 5 was less than it. Power 6 was greater. Now, take the range from 5 to 6 and start dividing it into smaller numbers and start searching from both sides until you find something very close. You will not be able to find the exact value because, again, these are real numbers, right? So you will just keep approaching it from both sides until you say that's enough error and stop at that point. Okay. And then you fill a table, right? The algorithms might be a little bit more efficient in terms of how they search from right and left and how they approach the problem to reduce the complexity, but in general, it's a complex problem. It's a number of computations required gets larger and larger as you deal with larger numbers, okay? Same thing for the discrete logarithm. The problem is not easy to solve. If you want to solve this equation, right, where you know g and you know x, it's easy to solve. You can find y. But if you know y and you know g and your task is to find x, the problem is very difficult. Because x in that case is the logarithm, right? If you want to find the power that you raise g to such that you get y, then in this case it's a logarithm. And solving this problem or solving this equation can only be done by something related to trial and error. There is no defined calculation method that will allow you to do this in one equation. Even the calculator. I mean, calculator can implement this with some approximation function. There are approximation functions, right? But generally speaking, it's not trivial to solve if you want to find the exact value or very close to the exact value. Okay?
Doctor, one might wonder why not just divide y by g multiple times until you get to the. So y divide g until you get to the lowest number.
Yeah, well, same thing. ما انت y divide g وبعدين at one point you will find that you divided by 5 g's, you divided by 6 g's. Which one? You don't know. It's somewhere in between. You keep searching in between, right? Same thing. It's similar to raising to the power. Same thing. Okay. Okay. So generally speaking, and it tells you that people who are working more into algorithmic complexity, they find that typically this is the number of computations, the order of the number of computations that you have to do in order to solve this problem, to find the logarithm. Now this tells you what? That as the base p grows, and as, so mainly, no, it looks like it's dependent only on the base p. So as your prime number that you use grows, this is gonna grow with a logarithmic raised to approximately here, it's a logarithmic raised to power 1 over 3, so that's approximately 1, and here it's a square logarithm, double logarithm inside and square logarithm. Okay, so that's generally it's an increasing function. As the number p increases, the complexity, the number of computation increases as well. Okay.
So this formula is for the complexity?
Yes. Complexity means an estimate of how many number of calculations or computations, assuming that a multiplication or an addition or a subtraction is just one step from operation. Okay?
To find a new prime number, it's in the millions or the billions or trillions or quadrillions.
It depends. As you go larger in the number scale,
The complexity just
yeah, exactly. Yeah. Okay, and here it just shows you some tables of logarithms. So the logarithm, the discrete logarithm of a to the base 2 and modulus 19. It shows you the value as for different values of a up there, 1, 2, 3, 4, 5, and so on. And then the value of the discrete logarithm itself in the lower, yes.
Dr. Neil, the order doesn't matter because of the mod.
Order مقصود بيه ايه؟
Right. Do you first do the log and then you do the modulus or the opposite?
Log and modulus. Ah, okay.
احنا we said it's a function of the modulus.
Here it's not calculated in orders here. It's a one-shot thing,
Okay.
right? Because you only need to. You actually need kind of build the table and try to raise to all powers, and then from there find the one that gives you the logarithm that you are looking for. So there is no kind of take the inside number and take it mod something or the outside number. There is no modding. Okay? The actual calculation goes the other way around. So you raise to powers, mod that number until you find the power that gives you what you are looking for. Okay? That's it. This. So simply to put it, why do we care about this? Because actually in the asymmetric, you can imagine how the operation happens, right? You pick two numbers, right? One of them is the private key, one of them is the public key. And those two numbers are a value and its discrete logarithm for the same base prime, right? And now what you do in encryption, you take the message and you raise it to the power of that public key and you send it, right? At the receiver, you take the received cipher and you raise it to the power of the logarithm of that, which is gonna bring it back to its original value, right? So simply it becomes the encryption and decryption process is just raising to the power. Just taking your message, raising it to some discrete power value, okay? And the relation between the private key and the public key is that one of them is the logarithm, the discrete logarithm of the other, right? So if I know the public key, it's not easy, if the public key is large enough, it's not easy actually to figure out the private key, okay? It's not as simplistic as that. There is some more like complexity operations similar to what we did in the block cipher description in the DES, such as doing some round and stuff and some more calculations, but that's the basic principle, okay? That you have two numbers, the relation between them is very complex, but using them for encryption and decryption is a simple process. Just raise to the power and again raise to the power, okay?
But doctor, why do you need discrete logarithms? Is it because it's harder to get to the prime? Or
because it provides, number one, it allows for that easy operation of encryption, decryption. Why are you running? We are still early.
I want to leave early.
Okay. Okay, go ahead. Okay. So number one, it makes the encryption and decryption easy process, just raising to power. And the way to do that is one of them has to be the discrete logarithm of the other, right? And the other nice property is that calculating the discrete logarithm is not easy. And these are the two properties that we want. Finding the private key from the public key has to be very hard. using the private or the public key for encryption and decryption has to be very simple. So that way we achieve simple calculation between the two trusted party, while the calculation that the non-trusted party has to do to break the system is very complicated. That's a secure system.
So
Right.
the one with, let's say, stronger GPUs has the advantage because he can do the calculations faster than the other.
But that's always the case. If any attacker has more powerful computation, then that attacker has a little bit more advantage. But what we are trying to do is not that. What we are trying to do is, if you want to communicate together securely, and you know one of you knows the private key, one knows the public key, right? The one who knows the public key can encrypt very quickly, does not need any computational power, very low computational power, which is just taking something and raising it to a power. That's a one step or a couple of steps calculation, right? And the other one is doing the same operation.
Okay.
Again, taking whatever it receives and raise it to a power. Thank you, done. Okay? So now we make it simple for trusted party, while anyone who wants to break the system, that one has to find the function of that one, or the mission of that one is it has to somehow find the private key from the public key, right? And if I want to find the private key from a public key, I need to perform discrete logarithm calculation, which is a very complicated process. If it takes a long time of calculation, it means that this guy is not going to break the system on time or with low cost, right? Okay.
And I thought maybe because let's say because we had the table there before, so maybe numbers are from 1 to 100 are defined already. So he just has to know which number that you're using, and that's it. He will find out.
No, but that's for very small numbers. For large numbers, even those tables do not exist.
Sure.
Okay.